Good morning. Today we will continue with the second moment of area. What we have just learned in the last class, solve some problem. Uh, uh, Let me quickly share my board and then look at what we were doing in the last class and continue today's class. Is that fine? Yeah. So I hope you are able to see this ActInspire board. So in the last class, we just began our class consolidating this important formulae. Though we were knowing that these formulas are obtained from applying first moment principle for these sections listed here, around 7 sections. So you see that the centroid, the application of first moment of area about an axis is to get the centroid of the section. So why the surface areas are very important is because in any of the components in mechanical system or in a building, there are beams, columns, and so on. So these all sections, if you look at, the sections properties are very important to characterize their load carrying capacity, characterize their stability, and so on. So in that perspective, as an engineer, these properties should be readily understood by you all, and then you would be able to apply them appropriately while solving design calculation for them. So that is why you have this particular module in our basic course, engineering mechanics course. So these listed formulas are can be used effectively. That's what we were looking at in a problem appearing here on the screen now. For finding out for a composite section, what do you mean by composite section? A composite section made of some standard geometrical section, added or subtracted and so on. So when you have like that composite section, it is not easy to locate immediately the centroidal coordinate of the section. Why? Because you are not having any axis of symmetry in this composite figure. If you have an axis of symmetry, then it is easy without applying first moment principle. By observation itself, you are able to say. That's all we have discussed. But in case of composite section where you do not have an axis of symmetry, obviously you require a reference to represent your composite section. So in this case, we have this XY axis set so that the entire composite is accommodated in first quadrant, and you are able to describe them with the standard geometries, and you are able to solve using the knowledge of the formulas for the standard geometries about this XY axis set, finding its first moments, and you solve this problem. So summation of first moments about x-axis for this composite area, and similarly about y-axis for this is what is going to help you to get your x bar and y bar respectively. That's what we were doing in this problem. Then we went on to the next lecture where we looked at what do you mean by second moment of area and its significance. There is something you are going to learn, very important concept called the pure bending equation. So this is m by I is equal to sigma by y is equal to E by R. So in this, you know what is m is the total bending moment value at a chosen section. I is second moment of area, sigma is bending stress, y is the layer that you consider from the neutral axis. Where is it located? So if you have to look at the beam bottom surface layer, then it is at the half the depth, d by 2 distance, and there you have your maximum bending stress. And neutral axis will have zero bending stress. So these are all something that you will be studying. What is E here is, E is what is called an Young's modulus. If this material is homogeneous material, isotropic material. What is R is, as you are applying this bending moment at the ends, so there will be deflection, and that beam will deflect in a circular arc, and that radius is what is R. So that would happen only in case of pure bending where couples only are acting. In non-uniform bending, you would see this curvature would change, right? However, this equation is very important equation as far as design of beams sections are concerned. So there you see that the bending stress is depends upon not only bending moment value at the section, the location of your layer. It is importantly depends upon second moment of area. So if this second moment of area is more, then you will have less bending stress. So it is going to carry more bending load. So that is the understanding. So you see that is the reason why you see the beams, the depth will be more than the top width. So that all we understood in the last class. And then how do you define this second moment of area mathematically is what we were just looking at. When you have this T section and its centroidal axis to locate, we first used our first moment principle. And then let me end as this. And then we were to find out the second moment of area about XC axis and YC axis. So for that, the definition of second moment of area is integral y squared dA. So where this elemental section goes from minus d by 2 to plus d by 2. So if I do this integration, I'm able to get this formula bd cube by 12. And similarly, one can also get IYC as x squared dA, and that become b cube d by 12. I asked you to work out this at your home, you could have done that. And we have also learned something called what is parallel axis theorem, and we proved that. That importantly, you should understand why this term has become 0. This term is 0 is because you see here integral y dA. Integral y dA is what is first moment about centroidal axis. So that is QXC. So first moment about centroidal axis should be 0. That is why this term is going out. And then you have this, so that has resulted into this. So what do you understand by that? If I have a section like this, and if I have to get about an axis, x-axis parallel to my centroidal axis, then it is simply sum of the second moment of area about the centroidal axis, IXC, what we derived for a rectangular section BD cube by 12, plus area into dy square. What is area? Is area of this section. Dy is the parallel distance between centroidal axis and the axis about which you are interested in finding out second moment of area. So that is how you would be able to apply this parallel axis theorem readily, right? So this is what you understood, and you are able to work out further for this T section, IXC and IYC. So IXC is what we were doing it. I asked you to complete this, and then you could have got this done. So now today I am going to start my lecture listing out an important formula for the second moment of area, like what we did in the previous day. And then we will solve another 1 or 2 problems, so that you would be familiar with any given section. How do you find out second moment of area, right? So let us just begin our today's class. This is lecture number 30, and today 14/04/2021. So